Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest and most quietly emotional stories in the history of space exploration, the story of Voyager, and the question of why humanity never truly built another mission like it again. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment letting me know where in the world you're listening from and what time it is for you right now. It is always comforting to see all the distant corners of Earth gathered together beneath the same night sky, each of us awake in our own little pocket of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let us gently begin. At this very moment, far beyond the planets, beyond Pluto, beyond the frozen debris fields at the edge of the solar system, two small machines are still travelling outward through the dark. Voyager 1 and Voyager 2, tiny spacecraft built in the 1970s, carrying less computing power than a modern digital watch, still whispering back to Earth from a distance so enormous that their signals need nearly a full day to arrive. And perhaps the strangest part of all is this: nothing is following them. No Voyager 3, no modern replacement drifting behind them, no newer spacecraft slowly catching up with better technology and brighter instruments. The farthest objects humanity has ever created are still artifacts of another era. It feels almost impossible when you stop and think about it carefully. Human beings crossed the entire outer solar system. We photographed volcanoes erupting on distant moons. We discovered hidden oceans beneath alien ice. We sent golden records carrying music and greetings into interstellar space itself. And then, somehow, we stopped. Not completely, of course. Humanity continued exploring. We built telescopes. We sent rovers to Mars. We placed orbiters around Jupiter and Saturn. We learned extraordinary things about the universe. But the specific kind of exploration represented by Voyager, the kind that quietly pointed itself toward the unknown and simply kept going farther, was never repeated. Tonight, we're going to explore why. And the answer turns out to be much stranger than most people realise. Because Voyager was not simply the product of advanced engineering, it was the product of timing. Not just technological timing, but planetary timing, political timing, cultural timing, even emotional timing. A brief moment when the planets themselves aligned and humanity aligned with them. The story begins, quietly enough, in 1964, long before launch, long before the golden records, long before the pale blue dot photograph. At the time, the outer solar system still felt unimaginably distant. Jupiter was little more than a striped sphere in telescopes. Saturn's rings appeared delicate and mysterious. Uranus and Neptune were barely more than pale, drifting lights against the darkness. No spacecraft had ever visited any of them. In those days, many scientists genuinely believed the outer planets might remain unreachable for generations. The distances were simply too large. Even light itself needed hours to travel there. A spacecraft launched directly toward Neptune using the rockets of the 1960s might need 30 years or more to arrive. And 30 years is a difficult thing for institutions to imagine clearly. Governments change, budgets shrink, engineers retire, entire careers pass by while a machine slowly drifts through silence. And yet, at NASA's Jet Propulsion Laboratory in California, a young graduate student named Gary Flandro was quietly working through orbital calculations. There was nothing glamorous about it, no dramatic control rooms, no rocket engines roaring into the sky, just graph paper, pencil marks, mathematics, and patience. His assignment sounded simple enough. plot the future positions of the outer planets and search for possible mission opportunities beyond Mars. Most people expected nothing unusual. The giant planets were scattered across billions of miles of emptiness. Reaching even one of them already seemed difficult enough. But as Flandro continued drawing their future positions year after year, decade after decade, a strange pattern slowly emerged across the page. The planets were moving toward alignment. Not a perfect straight line, but something close enough. Jupiter, Saturn, Uranus, Neptune, all drifting onto the same side of the Sun in a loose cosmic arc. The alignment was extraordinarily rare. It happens only about once every 175 years. The previous one had occurred before electricity existed, before railroads crossed continents, before photography, before human beings had ever flown through the sky. And the next would not come again until sometime in the 22nd century. But the alignment itself was not the true revelation. The real discovery was what gravity could do with it. Flandro realized a spacecraft might not need to carry enough fuel to reach every planet directly. Instead, it could borrow motion from the planets themselves. A spacecraft approaching Jupiter would fall into the giant planet's gravitational field like a skateboarder rolling into a massive curved bowl. As the spacecraft swung around the planet, Jupiter's motion around the Sun could fling it outward again at even greater speed. Then Saturn could do the same, then Uranus, then Neptune, each world becoming a stepping stone to the next. A chain reaction of motion across the outer darkness. Today we call this a gravity assist, but at the time it sounded almost unbelievable, like throwing a stone across a lake and somehow gaining speed after every bounce. Without this alignment, visiting Neptune might require 3 decades of travel. With it, a single spacecraft could potentially cross the outer solar system in only about 12 years. Suddenly, the impossible became merely very difficult. And something else became clear as well. The opportunity would not wait. The launch window would open in the late 1970s, and then quietly close again for nearly 2 centuries. It was as though the solar system itself had briefly unlocked a hidden doorway, offering humanity a narrow chance to step through. Miss it, and everyone alive at the time would be long gone before the doorway opened again. There is something strangely emotional about that realization. The planets do not care whether civilizations are ready. They continue their slow movements through darkness with perfect indifference. And every once in a while, if the timing is just right, the universe offers a path that will not exist again for generations. Somewhere inside a quiet office in California, surrounded by papers and calculations, a young student had accidentally discovered one of those paths. And although he could not fully know it yet, humanity's greatest journey into deep space had already begun to take shape, softly, silently, like the first faint glow of dawn appearing over a sleeping world. Once the mathematics became impossible to ignore, the atmosphere inside parts of NASA slowly began to change. What Gary Flandro had uncovered was not simply a clever route through the solar system. It was something far more unusual. For a brief moment in history, the architecture of the planets themselves appeared to cooperate with human ambition. And in the 1960s, ambition was everywhere. It is difficult now to fully recreate the emotional atmosphere of that era. The world felt larger than it does today, but strangely more reachable at the same time. Human beings were climbing into rockets for the very first time. Satellites circled overhead like mechanical stars. Nuclear energy promised nearly limitless power. Engineers spoke openly about cities beneath the ocean and colonies floating in space. The future seemed less like a mystery and more like a destination already rushing toward humanity at enormous speed. The moon landings had not yet happened when Flandro made his discovery, but the momentum toward them already felt unstoppable. Every year, rockets grew larger, computers became slightly smaller, machines travelled farther. Problems that once sounded absurd slowly became engineering challenges instead of impossibilities. And somewhere within this atmosphere of restless optimism, the idea of exploring all the giant planets in a single sweeping campaign began to feel achievable. At NASA's Jet Propulsion Laboratory, engineers and mission planners started imagining what became known as the Grand Tour. Even the name itself sounded enormous. Not a mission to one world, not a brief flyby of a single planet, but a coordinated journey across the entire outer solar system: Jupiter, Saturn, Uranus, Neptune. A machine moving from world to world like a traveller crossing distant kingdoms. The original concept was astonishingly ambitious. NASA hoped to build 4 large spacecraft. 2 would launch first and travel toward Jupiter, Saturn and Pluto. 2 more would follow on different trajectories toward Uranus and Neptune. The spacecraft were given a technical name that sounded far less romantic than the mission itself: Thermoelectric Outer Planet Spacecraft. Shortened to a collection of letters that engineers used comfortably, even if ordinary people rarely remember them now. But beneath the technical terminology was something genuinely extraordinary. For the first time in human history, scientists could realistically imagine surveying every giant planet within a single generation. It is important to remember how little humanity knew at the time. Today, images of Jupiter's storms or Saturn's rings feel familiar. They appear in textbooks, documentaries, phone wallpapers, and classroom posters. But in the 1960s, the outer planets were still deeply mysterious. No one knew what Neptune's atmosphere truly looked like. No one knew whether Uranus possessed rings. No one knew Io contained volcanoes. No one knew Europa hid the possibility of a buried ocean. No one had ever seen Titan's surface. No one had ever travelled beyond Jupiter at all. The outer solar system remained more imagined than understood. In a strange way, it resembled the old age of ocean exploration on Earth, when maps faded into empty parchment near the edges because nobody knew what waited farther west, and the Grand Tour promised to illuminate that darkness all at once. The engineering challenges were almost absurd for the era. The spacecraft would need to survive for more than a decade in deep space. That alone sounded nearly impossible. Most previous missions lasted only months or a few years before failing. They would need to navigate gravitational encounters with extraordinary precision. A tiny error near Jupiter could send a spacecraft drifting hopelessly off course forever. They would need to survive intense radiation surrounding giant planets, especially Jupiter, whose magnetic environment is so violent that it can damage electronics the way constant ocean waves slowly erode stone. And perhaps most frightening of all, the spacecraft would need to function largely alone. At Jupiter's distance, radio signals already required well over an hour for a round trip between Earth and spacecraft. By Neptune, the delay would stretch to many hours. If something failed, engineers could not simply grab a joystick and react instantly. The machines would need enough intelligence to protect themselves. This may sound ordinary today in an age of autonomous software and artificial intelligence, but at the time, it was revolutionary. And yet, despite all these obstacles, enthusiasm continued growing, because the reward felt almost mythical. A single generation of scientists could witness the unveiling of the entire outer solar system. There was also another emotional layer beneath the science, something quieter but equally powerful. The Grand Tour reflected the psychology of the Apollo era itself. During those decades, many people genuinely believed humanity stood at the beginning of a permanent expansion into space. Not a temporary adventure, not a brief political competition, but the opening phase of a larger future. Magazine illustrations showed rotating space stations drifting above Earth like enormous silver wheels. Artists painted cities beneath transparent domes on the moon. Engineers discussed nuclear rockets that might one day carry human beings toward Mars or even the outer planets. Looking back now, some of these visions feel naive, but there was something beautiful in that confidence. Civilizations occasionally experience moments when the future feels enormous and open, when technological progress appears to move in only one direction, outward. The Grand Tour belonged to that emotional climate. It was not merely a scientific proposal, it was an expression of how humanity imagined itself during that brief period in history. A species beginning to step into the wider universe, and for a little while, it truly seemed possible. Inside laboratories and conference rooms, trajectories were refined. Instrument concepts were discussed. Engineers imagined cameras peering through the haze of Titan and across the storms of Neptune. Some even spoke quietly about what might come afterward. Perhaps larger interstellar probes, perhaps nuclear-powered spacecraft, perhaps missions that would someday leave the solar system entirely. The future seemed to stretch endlessly forward, but history rarely moves in straight lines for very long. Even as the Grand Tour gained momentum, the forces supporting it were already beginning to weaken. Because beneath the optimism of the 1960s, another reality was slowly approaching. The Apollo program was becoming unimaginably expensive. Political priorities were shifting, public attention was drifting, economic pressures were growing heavier. And although few people fully realized it yet, the extraordinary outward momentum that carried humanity to the moon was already beginning to slow, like a wave losing energy before it reaches the shore. The planets remained aligned in silence, patiently waiting. But the civilization hoping to reach them was quietly changing underneath its own dreams. In July of 1969, human beings stood on the moon for the very first time. For a few brief days, it felt as though history itself had accelerated. Millions of people gathered around televisions late into the night, staring at blurry black and white images transmitted across nearly 250,000 miles of space. Families sat together in dark living rooms, listening to crackling voices from another world. Children who watched the landing would later describe the experience almost like witnessing mythology, becoming real in front of them. A human footprint pressed softly into lunar dust, and for a moment, it seemed there was almost nothing humanity could not do next. The atmosphere surrounding the Apollo missions is difficult to describe now because modern spaceflight often feels quieter and more routine. But during those years, the moon landings carried the emotional intensity of a civilization proving something to itself. The United States and the Soviet Union were locked inside the enormous psychological tension of the Cold War. Rockets were not just machines, they were symbols of ideology, intelligence, industrial strength, and national destiny. Space became a stage where entire political systems tried to demonstrate superiority, and Apollo succeeded magnificently. The Saturn V rocket remains one of the most powerful machines ever built. When it launched, the ground itself trembled beneath spectators standing miles away. Windows rattled, air vibrated in people's chests, birds scattered from nearby marshes in frightened clouds. It didn't merely look powerful, it felt geological, like a controlled volcano carrying human beings upward into the sky. But triumphs of that scale create strange problems afterward, because once a civilization achieves what once seemed impossible, it must decide whether the extraordinary effort should continue, and continuing is often much harder than beginning. By the early 1970s, the emotional momentum that fueled Apollo had already begun to weaken. Part of this was political. The United States had won the symbolic race to the moon. The urgency that justified enormous spending suddenly felt less immediate. Presidents changed, congressional priorities shifted, public attention drifted toward economic problems, social unrest, inflation, and the ongoing war in Vietnam. And part of it was psychological. Human beings adapt surprisingly quickly to miracles. The first moon landing stunned the world. The second still felt extraordinary. By the sixth, television ratings had already begun falling. There is something almost sad about that. A species walks on another world for the first time in 4 billion years, and only a few missions later, some people quietly stop paying attention. NASA's budget reflected this change with painful clarity. At the height of Apollo, NASA received roughly 4% of the entire United States federal budget. Money flowed into research centers, contractors, universities, launch facilities, and engineering programs at a scale almost impossible to imagine today. But after the moon landings, the numbers began shrinking rapidly. Year after year, funding slowly declined. Programs were cancelled, missions disappeared, factories closed. Thousands of workers lost their jobs. Even several planned Apollo moon missions were abandoned entirely. Massive Saturn rockets that had once represented the future stood unused inside storage buildings like relics from a civilization already fading into memory. And somewhere within this tightening financial atmosphere, the Grand Tour began entering dangerous territory. Because ambitious exploration missions become vulnerable the moment societies stop feeling emotionally connected to them. The Grand Tour was magnificent on paper, but also expensive, technically risky, and politically difficult to explain during an era of shrinking budgets. To many government officials, sending multiple spacecraft across the outer solar system sounded less urgent than domestic economic concerns back on Earth. And unlike Apollo, the Grand Tour lacked a dramatic geopolitical deadline. No rival nation was expected to reach Neptune first, no flag would be planted, no astronauts would step onto distant soil in triumph. The mission promised knowledge, wonder, and long-term scientific discovery. But those are often harder things to defend politically than immediate victories, especially because Voyager required patience. A great deal of patience. Some of its scientific rewards would not arrive until more than a decade after launch. Politicians approving the mission might already be retired before the spacecraft even reached Neptune. That kind of timescale sits awkwardly inside modern political systems, which often think in election cycles lasting only a few years. There is an old saying that societies grow strong when people plant trees whose shade they know they will never sit beneath. Deep space exploration works very much the same way. The people who begin such journeys often understand that the greatest rewards may belong to future generations they will never meet. And yet, during the early 1970s, that kind of long horizon thinking was becoming increasingly difficult to sustain. NASA itself faced an uncomfortable identity crisis. The agency had been built around the urgency of Apollo. Entire teams, facilities, and engineering cultures existed because the United States wanted to reach the moon before the Soviet Union. But now the race was over. What came next? Some envisioned permanent moon bases. Others imagined missions to Mars. Still others argued for space stations, reusable spacecraft, or robotic exploration. There was no longer a single clear direction. The enormous outward momentum of the 1960s began fragmenting into competing visions of the future, and amid all this uncertainty, one fact became increasingly impossible to ignore. NASA could no longer afford to do everything. Choices would have to be made, quietly, almost invisibly. The future of the Grand Tour began depending less on scientific excitement and more on political survival. It is strange to realise how fragile great exploration eras can be. Looking backward, history often makes them appear inevitable. We imagine humanity steadily marching outward toward greater knowledge, as though progress naturally continues forever. But reality is softer and more uncertain than that. Exploration depends on budgets, on public imagination, on political timing, on institutional confidence, on whether enough people believe the future is worth investing in. And these conditions do not remain stable forever. Sometimes they align beautifully for a few brief years, and sometimes, almost without anyone noticing at first, they begin to drift apart again. While NASA struggled to redefine itself after Apollo, the planets continued moving silently through space, maintaining the rare alignment Gary Flandro had discovered years earlier. The window remained open, but not for long, and soon NASA would make a decision that quietly changed the future of deep space exploration for generations to come. By the early 1970s, NASA stood at a crossroads. The moon race had ended, Apollo was fading, budgets were shrinking, and inside government offices and engineering centres across the United States, a difficult question slowly became unavoidable. What should the future of space exploration actually look like? For a while, the answer seemed almost limitless. Some engineers still dreamed of human missions to Mars. Others imagined giant rotating stations orbiting Earth like artificial worlds. There were proposals for lunar cities, nuclear rockets, reusable spacecraft, and permanent scientific colonies scattered throughout the solar system. But dreams become fragile when they encounter accounting offices. And NASA's leadership understood something painful. The agency no longer had enough money to pursue every future at once. Choices had to be made. Among all the competing visions, one concept slowly gathered political momentum above the others: the space shuttle. At first glance, the shuttle sounded practical, even revolutionary. Instead of building rockets that were discarded after a single launch, NASA proposed creating a reusable spacecraft that could fly repeatedly between Earth and orbit, a kind of cosmic transportation system, something more routine, more sustainable, less dramatic than Apollo perhaps, but more permanent. The idea appealed strongly to politicians. Reusable sounded economical, operational sounded responsible. Near-Earth missions felt easier to justify than decade-long journeys toward distant planets. And emotionally, the shuttle represented a different philosophy of spaceflight. Apollo had been about reaching outward toward a distant destination. The shuttle was about building infrastructure closer to home. This distinction mattered far more than people realized at the time, because institutions slowly become shaped by the kinds of missions they perform most often. Apollo trained NASA to think boldly, to accept uncertainty, to move quickly, to chase difficult objectives across enormous distances. But the shuttle required something different: routine operations, reliability, schedules, maintenance, frequent launches, safety reviews, careful political oversight. Over time, NASA itself began changing around these new priorities. The agency that once hurled astronauts toward the moon was gradually transforming into something more operational, more cautious, more focused on low Earth orbit. And somewhere in the middle of this institutional transformation sat the Grand Tour. Huge, expensive, slow, risky, difficult to explain politically, exactly the kind of mission vulnerable during times of uncertainty. In its original form, the Grand Tour would have required multiple large spacecraft travelling across the outer solar system over many years. The cost estimates frightened policymakers already anxious about shrinking budgets. And so, quietly, the cuts began. First, the mission was reduced, then simplified, then delayed, then reconsidered again. Eventually, the original Grand Tour program was cancelled almost entirely. It is strange to think about now. One of the greatest exploration opportunities in human history nearly vanished, not because the science was unimportant, but because civilizations are always balancing competing futures against one another. In many ways, Voyager survived only because some engineers and planners refused to completely let go. Inside NASA and the Jet Propulsion Laboratory, smaller replacement concepts slowly emerged from the wreckage of the cancelled Grand Tour. If 4 spacecraft were impossible, perhaps 2 might survive. If the full mission was too expensive, perhaps a stripped-down version could still work. If politics demanded compromise, perhaps compromise could at least preserve part of the dream. And so, the mission that eventually became Voyager was born less from confidence than from adaptation. That detail matters. History often remembers Voyager as an inevitable triumph. Looking backward, it feels natural that humanity would send spacecraft across the giant planets. But from inside the moment itself, nothing felt guaranteed. The mission existed in a state of near constant vulnerability. Funding meetings, redesigns, political negotiations, technical compromises. At times, Voyager resembled a ship being rebuilt while already drifting away from shore. And yet, something remarkable happened during this period. The engineers began quietly designing the spacecraft to survive far longer than officially required. Publicly, the missions were justified mainly around Jupiter and Saturn. Few policymakers wanted to fund machines expected to operate for decades, but many of the people actually building the spacecraft suspected something else might be possible. If Voyager remained healthy, if the gravity assist worked, if the electronics survived, if enough fuel remained, perhaps the spacecraft could continue far beyond Saturn, maybe all the way to Uranus, maybe even Neptune. So the spacecraft were built with hidden endurance. Not infinite endurance, of course. No machine lasts forever, but resilience, backup systems, redundant electronics, protective fault management, software capable of responding autonomously when signals from Earth arrived too slowly to help. This was especially important because of distance. Even near Jupiter, radio messages already travelled for many minutes before reaching Earth. By the time Voyager eventually approached Neptune, communication delays would stretch toward half a day for a round trip. The spacecraft needed enough intelligence to protect themselves in loneliness. There is something deeply human about that idea. Machines launched by people who understood they could not always be there to guide them. Like parents teaching children how to survive independently before sending them far from home. Meanwhile, outside NASA, the broader world continued changing. Economic instability spread through much of the 1970s. Inflation rose. Oil crises disrupted economies. Public trust in institutions weakened after years of war and political scandal. The cultural mood that once fueled Apollo's giant ambitions slowly became more cautious, more inward-looking. And this changing emotional atmosphere affected space exploration too. The future no longer felt endlessly expansive. It felt uncertain. In hindsight, Voyager now appears almost like the final echo of an earlier era, one last outward breath from the civilization that landed on the moon. Because while the shuttle looked inward toward Earth orbit and reusable infrastructure, Voyager still looked outward into darkness, toward the unknown, toward distance, toward worlds no human being had ever truly seen. And perhaps most remarkably of all, it was still alive, barely funded, reduced in scope, constantly threatened, but alive. The planets continued moving into alignment beyond the windows of Earth, waiting silently for launch opportunities that would not return again for nearly 2 centuries. And deep inside, laboratories filled with wires, diagrams, and quiet determination, 2 small spacecraft were slowly taking shape, carrying with them not only cameras and instruments, but the fading momentum of an entire age of optimism. As the Voyager spacecraft slowly took shape during the 1970s, there was a quiet understanding among many of the engineers working on them. Officially, the missions only needed to survive long enough to complete their encounters with Jupiter and Saturn. That alone would already be historic. Anything beyond that was uncertain. But uncertainty has a strange effect on imaginative people. Sometimes it discourages them, and sometimes it quietly inspires them to prepare for possibilities nobody is fully willing to discuss out loud. Inside laboratories at the Jet Propulsion Laboratory in California, engineers began designing the spacecraft with a kind of cautious optimism hidden beneath the official mission requirements. Not extravagance, not recklessness, resilience. If a component failed, perhaps another system could take over. If communication weakened, perhaps the spacecraft could protect itself temporarily. If fuel needed to be conserved, perhaps tiny adjustments could preserve years of additional life. The philosophy was simple in spirit, even if the engineering itself was extraordinarily difficult. Build carefully, waste nothing, assume the spacecraft will one day be alone. There is something quietly beautiful about engineering designed around loneliness. Voyager would travel farther from Earth than any machine in history. Eventually, the spacecraft would become so distant that even radio messages moving at the speed of light would require many hours to cross the darkness between worlds. No rescue missions would ever come. No astronaut would ever repair damaged equipment. No replacement parts would arrive drifting through space. Whatever Voyager carried at launch would be all it possessed for the rest of its existence, and so the spacecraft were designed almost like deep-sea vessels crossing an ocean too large for rescue ships to follow. Every watt of electricity mattered, every gram of fuel mattered, every command sent from Earth mattered. Even the computers reflected this philosophy of efficiency. Today, modern phones carry processing power so enormous that most people rarely think about it. A simple photograph now contains more digital information than Voyager's entire computer memory. The spacecraft possessed only tiny amounts of storage by modern standards. Their memory would seem almost impossibly small today, less than what many electronic greeting cards quietly contain. And yet, those limited computers guided two spacecraft across billions of miles of space. There is a lesson hidden inside that contrast. Modern technology often grows more powerful by becoming more complex. But complexity carries weight. Complexity increases costs. Complexity creates more opportunities for failure. Voyager belonged to a different engineering era, an era where limitations forced elegance. The spacecraft could not rely on enormous computational resources, so engineers instead built systems that were lean, purposeful, and remarkably durable. In some ways, this simplicity became one of Voyager's greatest strengths. The spacecraft were also powered in a very unusual way. Near Earth, satellites can use sunlight for electricity through solar panels. But Voyager would travel far beyond the warmth of the inner solar system, into regions where sunlight becomes weak and thin, more like faint twilight than daylight. At Neptune's distance from the Sun, sunlight is hundreds of times dimmer than it feels on Earth. Solar panels large enough to operate efficiently there would have been impractical for the mission. So Voyager carried a different kind of power source, small nuclear generators. Inside them rested a radioactive material called plutonium-238. As the material naturally decayed, it released heat. The spacecraft converted some of that heat into electricity through devices called radioisotope thermoelectric generators. The name sounds complicated, but the idea itself is surprisingly gentle. Tiny pieces of warmth slowly becoming electricity, like embers in a fireplace continuing to glow long after the flames themselves have faded. These generators gave Voyager something priceless: longevity. Not unlimited power, of course. Every year the plutonium's energy output slowly declined. The spacecraft would gradually weaken over time, like lanterns dimming during a very long night. But the decline was slow enough that the mission might continue far beyond Saturn if everything else survived. And so the engineers prepared for endurance. The spacecraft carried backup thrusters, backup communication pathways, backup timing systems. Even the golden records attached to Voyager reflected this mindset of permanence. The records were not designed for a quick exchange. They were built to survive deep time itself, protected inside golden metal covers against the cold silence of interstellar space. There is something deeply emotional about imagining the people who assembled these machines. Many were young engineers during Apollo. They had grown up in an age when technological progress seemed limitless. Rockets improved every year. Missions expanded farther outward. Humanity appeared to be accelerating into the future. But by the time Voyager was being built, the atmosphere had already begun changing. Budgets tightened, programs disappeared, optimism softened into caution, and perhaps because of this, some engineers quietly suspected Voyager might become something rare. Not merely another mission in a continuous chain of exploration, but possibly the last mission of its kind for a very long time. So they built carefully, they tested relentlessly, they simplified where possible, they prepared for failure constantly. And strangely enough, this acceptance of fragility may have helped Voyager survive. There is a tendency in modern culture to imagine great achievements emerging from certainty and confidence. But many of humanity's most enduring creations come from people who understand uncertainty deeply. Voyager's engineers expected things to go wrong eventually. The question was never whether problems would appear. The question was whether the spacecraft could adapt gracefully enough to continue moving forward anyway. That philosophy would become essential later, when engineers on Earth found themselves reviving damaged thrusters decades after launch, rewriting software for computers older than many of the people operating them, and listening carefully for signals so faint they resembled whispers, dissolving into cosmic static. But all of that still lay in the future. For now, the spacecraft rested on Earth beneath bright lights and scaffolding, surrounded by technicians making final adjustments before launch. Soon, they would leave forever. Soon, they would begin crossing distances so enormous that Earth itself would shrink into a pale star behind them. And somewhere beyond the noise of politics, budgets, and institutional uncertainty, the outer planets continued waiting in silence, arranged briefly along a pathway that would not appear again for generations. In the late summer of 1977, Voyager 1 and Voyager 2 finally left Earth. The launches themselves were thunderous. Enormous rockets climbing through clouds while flames spread beneath them like artificial suns. Crowds gathered to watch from beaches and roadsides in Florida, staring upward as the spacecraft began journeys no machine had ever attempted before. And then, gradually, the noise faded. That is one of the strange things about deep space exploration. The launch feels dramatic and immediate, but the actual mission unfolds slowly, almost quietly, over years and decades. After the excitement of departure, Voyager entered the long silence between worlds. The spacecraft drifted outward through darkness while Earth itself continued changing behind them. Presidents came and went. Children grew older. Entire television shows began and ended. Seasons passed across continents again and again while the tiny probes continued patiently crossing the solar system. For more than a year after launch, Jupiter still remained far ahead, and yet even from a distance, the giant planet already seemed enormous. Jupiter is difficult to describe properly because it barely resembles ordinary intuition. It is so large that more than 1,000 Earths could fit inside its volume. Its magnetic field is immense. Its storms are larger than entire planets. Around it travels a miniature solar system of moons, each one a separate world. Before Voyager arrived, scientists expected Jupiter to be fascinating, but they still imagined it as a relatively stable place. Beautiful perhaps, but predictable. What Voyager discovered instead was motion, violence, heat, activity, change. The spacecraft approached Jupiter in 1979, and as the images began arriving on Earth, scientists found themselves staring at something almost alive in its complexity. Cloud bands wrapped around the planet in enormous rivers of colour. Storm systems twisted together in layered turbulence. Lightning flashed deep inside the atmosphere. The Great Red Spot, a storm larger than Earth itself, churned across the planet like a rotating continent of wind. But perhaps even more surprising than Jupiter itself were the worlds orbiting around it, especially a moon called Io. Before Voyager, most scientists assumed small moons in the outer solar system would be ancient, frozen, and geologically dead, worlds shaped long ago and left unchanged for billions of years. Io shattered that assumption completely. As Voyager's images sharpened, scientists noticed strange discolorations across the moon's surface. Then they noticed towering plumes rising above the horizon. Volcanoes, not ancient volcanoes frozen in time, but active eruptions happening at that very moment. It was the first time humanity had ever witnessed volcanic activity beyond Earth. The discovery stunned planetary scientists. Io was not quiet, it was restless. Its surface looked stained with sulfur in shades of orange, yellow, red, and black, almost like glowing embers scattered across snow-darkened stone. Some eruptions blasted material hundreds of miles above the moon before it slowly drifted back downward. The moon appeared less like a frozen rock and more like a wound that had never fully cooled, and the explanation behind Io's volcanoes turned out to be just as strange. Jupiter's gravity constantly squeezed the moon as it orbited nearby. The immense gravitational pull stretched and compressed Io over and over again, generating heat deep inside the moon's interior, like endlessly bending a paperclip until it becomes hot, except on a planetary scale. And suddenly, scientists realized something profound. The outer solar system was not simply a graveyard of frozen worlds. Energy existed there too. Movement existed there too, possibly even environments where life might someday emerge. That possibility became even more intriguing when Voyager examined another moon nearby, Europa. At first glance, Europa looked calm compared to chaotic Io. Its surface appeared pale and smooth, covered in long, dark fractures stretching across ice like cracks spreading through frozen lakes during winter. But the more scientists studied those patterns, the stranger Europa became. There were very few impact craters. That mattered enormously. Cratered surfaces reveal age. Worlds exposed unchanged for billions of years slowly accumulate scars from impacts across time. But Europa's surface looked unexpectedly young, as though something had resurfaced it repeatedly. Something beneath the ice. Scientists began considering a possibility that once sounded almost absurd. Perhaps beneath Europa's frozen crust rested a vast hidden ocean kept liquid by internal heat. A dark ocean buried beneath miles of ice, far from the warmth of the sun. Today, Europa is considered one of the most promising places in the solar system where simple life might potentially exist. Entire future missions have been planned around studying this possibility more carefully, but the first clues arrived quietly through Voyager's cameras, and that pattern repeated itself again and again during the mission. Voyager kept discovering things nobody had specifically gone looking for. This may actually be one of the mission's most important legacies. Modern scientific missions are often designed around very focused questions. engineers and scientists spend years carefully defining precise objectives before launch. But Voyager belonged to an earlier style of exploration, a broader style, a survey mission. The spacecraft simply looked carefully at worlds humanity had never seen closely before, and reality turned out to be stranger than prediction. There is something deeply valuable in that kind of exploration, because sometimes the greatest discoveries are not answers, sometimes they're surprises, sometimes they're entirely new questions impossible to ask before you realize certain worlds even exist. As Voyager continued moving through the Jovian system, scientists also observed delicate rings surrounding Jupiter, something nobody expected to find there at all. The giant planet's moons revealed wildly different personalities. Ganymede carried enormous grooves and ridges across its icy surface. Callisto appeared ancient and heavily scarred, like an artifact from the solar system's earliest years. Everywhere Voyager looked, complexity unfolded, and slowly the emotional atmosphere surrounding the mission began changing. Voyager was no longer merely a technological achievement. It was becoming something else, a revelation. The outer solar system was not empty. It was alive with weather, chemistry, geology, movement, and mystery beyond anything scientists had confidently predicted before launch. And somewhere inside mission control rooms filled with glowing screens and printed data sheets, people began realizing something extraordinary. Humanity had waited thousands of years to see these distant worlds properly for the first time, and now, at last, the darkness was beginning to open. After Jupiter, the spacecraft continued outward, farther from the warmth of the sun, farther from Earth, farther into regions of space where sunlight weakened into a pale and distant glow. Ahead waited Saturn. Even today, Saturn carries a strange emotional effect on people. There is something almost unreal about it. The planet seems less like an ordinary world and more like a dream that somehow exists physically in the universe. Its rings appear impossibly delicate, thin bands of brightness suspended around a giant sphere of gas and storms. For centuries, human beings could only glimpse Saturn through telescopes, a distant ornament in the sky, beautiful but unreachable. And then Voyager arrived. As the spacecraft approached in 1980, Saturn slowly expanded inside its cameras until the planet filled the darkness with gold, cream, amber, and shadow. The rings became astonishingly detailed. Thousands of individual ringlets emerged where earlier telescopes saw only broad bands of light. Some appeared braided together, others carried strange gaps and waves. Tiny moons drifted among them like shepherds guiding rivers of ice. The rings looked solid from a distance, but Voyager revealed something subtler. They were made mostly of countless fragments of ice and rock, particles ranging from dust grains to pieces as large as mountains, all orbiting Saturn together in extraordinary balance. It is difficult not to feel poetic when looking at Saturn's rings for too long. They resemble the visible shape of gravity itself, motion made beautiful. And yet, as extraordinary as Saturn appeared, another target quietly dominated scientific attention: Titan. Saturn's largest moon had fascinated astronomers for decades because of one unusual fact. Titan possessed a thick atmosphere. That alone made it extraordinary. Most moons in the solar system are too small to hold dense atmospheres for long periods of time. Their gravity is too weak. Gases slowly escape into space across millions of years. But Titan remained wrapped in a heavy orange haze. Scientists suspected that beneath those clouds might rest one of the most Earth-like environments in the outer solar system, at least in terms of atmospheric complexity. No one knew exactly what Voyager would find there, and that uncertainty created a difficult choice: the trajectory allowing the best close-up study of Titan, would permanently redirect Voyager 1 upward and out of the flat planetary plane where the giant planets orbit. In practical terms, this meant Voyager 1 could either continue the grand tour toward additional planets or investigate Titan closely, but not both. It was one of the most important navigational decisions of the entire mission, and in a quiet room filled with calculations, mission planners chose Titan. The scientific opportunity felt too important to ignore, so Voyager 1 descended toward the moon. As the spacecraft approached, Titan slowly revealed itself, though never completely. Thick orange smog concealed the surface beneath layers of atmospheric haze. Sunlight filtered weakly through hydrocarbons suspended in the air, giving the moon an appearance almost like a world hidden behind permanent sunset. Voyager discovered an atmosphere denser than many scientists expected. Rich in nitrogen and filled with complex organic chemistry. Winds moved through the haze. Methane existed in the atmosphere. Chemical reactions unfolded high above the hidden surface. It was not Earth, of course. Titan was unimaginably cold. Temperatures there are cold enough that water behaves almost like stone. But methane and ethane can exist as liquids under those conditions. In some strange way, Titan resembled a distorted reflection of Earth, an alien version of weather. Today we know Titan possesses lakes, rivers, rainfall and seas made not from water, but from liquid hydrocarbons. Future missions may someday even send flying drones through its thick atmosphere. But Voyager provided humanity's first true glimpse into that mysterious world. And then, after Titan, Voyager 1 turned away. Its path bent upward above the planetary plane forever. The spacecraft would never visit another planet again. Instead, it began a different journey. A slower one, a lonelier one, a journey toward interstellar space itself. There is something unexpectedly emotional about this moment in the Voyager story. The spacecraft had spent years moving from world to world, each destination revealing new wonders: Jupiter's storms, Io's volcanoes, Europa's ice, Saturn's rings, Titan's haze, and then suddenly, the planets began falling behind. One by one, the bright spheres shrank into distant points of light. Voyager 1 quietly departed the familiar architecture of the solar system and entered the long darkness beyond. Meanwhile, Voyager 2 continued onward alone. This was always part of the broader strategy. Because Voyager 2 launched first on a slower trajectory, it remained positioned to continue toward Uranus and Neptune after Saturn. But now the emotional meaning had changed. Voyager 1 became humanity's first interstellar traveller. Voyager 2 became the final surviving explorer of the Grand Tour. Everything depended on it remaining alive, and by this point, the mission had already surpassed expectations dramatically. The spacecraft had survived Jupiter's intense radiation. Its instruments continued functioning. The gravity assists worked beautifully. Fuel reserves remained usable. Communication systems still whispered faithfully across enormous distances. The engineers who quietly overbuilt the spacecraft years earlier were beginning to realize something remarkable. Voyager might truly reach the edge of the solar system, not metaphorically, not symbolically, literally. There is an image Carl Sagan later described that captures this emotional shift beautifully. He spoke of Voyager as humanity becoming ocean-going. For most of history, civilizations remain close to familiar shores. They travel cautiously along coastlines they understand. But eventually some cultures begin crossing open water toward places nobody has ever seen before. Voyager carried that same feeling into space. The spacecraft were no longer simply visiting planets. They were beginning to leave home. And somewhere behind them, Earth continued shrinking into a tiny pale world, orbiting an ordinary star among hundreds of billions scattered across the galaxy. The farther Voyager travelled, the more fragile and isolated humanity itself began to seem. Not weak exactly, but small. Small in the way a candle flame is small beneath a night sky filled with stars, and yet perhaps more precious because of that smallness. As Voyager 1 drifted into deeper darkness, and Voyager 2 aimed itself toward the unknown ice giants ahead, the mission slowly transformed from a scientific expedition into something quieter and more philosophical. A meditation on distance, on time, on loneliness, on curiosity strong enough to cross billions of miles of emptiness, simply to see what waits there. And far ahead, beyond Saturn's fading glow, Uranus and Neptune still circled silently in darkness, worlds no human machine had ever approached before. By the time Voyager 2 left Saturn behind, the mission had already entered territory no spacecraft was ever originally guaranteed to reach. Years earlier, even surviving long enough to encounter Jupiter and Saturn had seemed ambitious. Now Voyager 2 continued outward alone into regions of darkness almost nobody on Earth had ever truly imagined in detail. The distances became difficult for the human mind to hold comfortably. Sunlight weakened steadily. Radio signals took longer and longer to cross the emptiness. The spacecraft itself shrank into a tiny moving point surrounded by billions of miles of silence. And ahead waited Uranus. Even today, Uranus remains one of the strangest major planets in the solar system, partly because it behaves unlike almost anything else nearby. Most planets rotate somewhat upright relative to their orbit around the Sun, but Uranus appears tipped dramatically onto its side, almost as though some ancient cosmic collision knocked the planet over long ago. As a result, its seasons become almost surreal. For long stretches of time, one pole points nearly directly toward the Sun while the opposite pole remains trapped in darkness. Decades of daylight, decades of night. The planet itself also looked strangely calm through telescopes before Voyager arrived. Compared to Jupiter's storms or Saturn's dramatic rings, Uranus appeared pale, quiet, almost featureless. But Voyager had already taught scientists an important lesson. Distant worlds often become stranger the closer you look. The spacecraft finally reached Uranus in 1986 after travelling for nearly 9 years through space. By then, many people who watched Voyager launch were already living entirely different lives. Children had grown into adults. Engineers who helped build the spacecraft were approaching retirement. And still, Voyager continued moving outward patiently, carrying a fading but persistent human presence into the dark. As the first detailed images of Uranus arrived on Earth, scientists immediately encountered surprises. The planet's atmosphere appeared subtle and muted at first glance, soft blue-green clouds suspended inside cold sunlight. But hidden beneath that calm appearance was a deeply unusual magnetic field. Instead of aligning neatly with the planet's center and rotation, Uranus possessed a magnetic field tilted dramatically off-angle, lopsided and strangely unstable. It behaved less like the smooth magnetic structure scientists expected, and more like a wobbling lantern swinging through darkness. No one fully predicted it, and once again, Voyager reminded humanity that the universe is under no obligation to resemble human assumptions. The moons of Uranus also revealed landscapes unlike anything previously imagined. Miranda, one of the strangest, looked almost broken apart and reassembled. Giant cliffs towered, across its surface beside fractured terrain that resembled pieces of entirely different worlds stitched together unevenly. Some scientists compared it to a shattered object, frozen after violent reconstruction. It was another reminder that the outer solar system was not static. These worlds carried histories, violence, transformation, internal activity, ancient catastrophes. Even at the edge of the Sun's domain, change still shaped planets and moons across unimaginable spans of time, And yet, astonishingly, Uranus was only the second to last destination. Farther still waited Neptune. No spacecraft had ever travelled so deep into the solar system before. The journey from Uranus to Neptune alone required another 3 years. 3 years drifting farther from warmth, farther from sunlight, farther from the familiar architecture of the inner planetary system. And somehow, Voyager survived it. There is something remarkable about that endurance. The spacecraft crossed billions of miles carrying technology designed during the 1970s. Tiny computers, aging thrusters, gradually weakening nuclear generators, and still the machine kept functioning, like an old ship somehow surviving storms far beyond the horizon where anyone expected it to sail. Voyager finally arrived at Neptune in 1989. To this day, it remains the only spacecraft ever to visit the planet. That fact alone feels strangely emotional. Humanity reached Neptune once, briefly, and then never returned. As the images arrived, Neptune revealed itself not as a quiet frozen sphere, but as a dynamic world filled with violent weather. Dark storms swirled across its atmosphere. White clouds streaked through high-altitude winds. Some winds moved faster than the speed of sound on Earth. At such enormous distances from the Sun, scientists expected Neptune to possess little remaining atmospheric energy. Sunlight there is extremely weak, more like a distant glimmer than true daylight, and yet the planet remained active, restless, alive with motion. It was another reminder that planetary systems are more complicated than simple temperature alone. But perhaps the most haunting discovery waited beyond Neptune itself, a moon called Triton. Triton immediately appeared unusual because it orbited Neptune backward compared to the planet's rotation. Scientists suspected it was not originally Neptune's moon at all, but a captured object pulled inward long ago from the outer darkness beyond the planets. And Voyager revealed a surface unlike almost anything previously seen. Triton appeared pale and frozen, covered in nitrogen ice, and strange terrain shaped by mysterious geological forces. But then scientists noticed something astonishing. Dark plumes rising from the surface, geysers. Even here, at the edge of the solar system, the activity still existed. The universe refused to become simple. There is a beautiful pattern hidden throughout the Voyager mission. Again and again, the farther humanity travelled from Earth, the more complexity it discovered, not less. The outer darkness did not become empty. It became stranger, more layered, more surprising, more alive with hidden processes unfolding beneath ice, storms, gravity, and time. And then, after Neptune, the grand tour finally ended. No more planets waited ahead. Voyager 2 continued outward into the black beyond Neptune while mission scientists slowly confronted a strange emotional reality. Humanity had completed its first exploration of the giant planets, and humanity had no immediate plans to do it again. The years passed. New missions would later return to Jupiter and Saturn in greater detail. Orbiters would study their moons for decades. New Horizons would eventually visit Pluto far beyond Neptune. But Uranus and Neptune remained untouched. No orbiter followed Voyager. No atmospheric probes descended into their clouds. No landers explored their moons. Even now, nearly 4 decades later, most of humanity's detailed knowledge about the ice giants still comes from a few fleeting hours during Voyager 2's flybys in the 1980s. It is difficult not to feel a quiet sadness in that realization. An entire generation of planetary science opened briefly, and then paused. Somewhere in the darkness tonight, Voyager 2 is still travelling outward beyond the planets it once revealed to humanity for the first time, and behind it, the outer solar system remains largely unexplored, once more, vast, silent, and waiting. When Voyager 2 passed Neptune in 1989, there was a quiet feeling among many scientists that humanity had crossed an invisible threshold. For the first time in history, every major planet in the solar system had been visited by human-made spacecraft. The achievement felt immense. Over little more than a decade, Voyager had transformed the outer planets from distant points of light into real places filled with storms, volcanoes, ice fractures, chemical haze, magnetic chaos, and hidden oceans. Entire textbooks had to be rewritten. New scientific fields expanded almost overnight. Questions nobody previously imagined suddenly became central mysteries of planetary science. And perhaps most importantly of all, Voyager worked. Not merely adequately, not barely, magnificently. The spacecraft survived radiation, distance, extreme cold, communication delays, and years far beyond their original expectations. Their instruments continued returning discoveries long after many engineers assumed the missions might already have failed. To many people, it seemed obvious what would happen next. Surely humanity would build something even more ambitious. After all, this is normally how technological history appears to unfold. The first airplanes seem primitive. Then larger and faster aircraft follow. Early computers evolve into more powerful machines. The first rockets lead to bigger rockets. One generation builds the foundation, and the next extends it farther outward. And so, after Voyager, many scientists and ordinary citizens quietly assumed another great deep space survey mission would eventually emerge. Perhaps not immediately, but soon enough. Maybe a more advanced Grand Tour. Maybe orbiters for Uranus and Neptune. Maybe even interstellar probes designed specifically to leave the solar system entirely. The future still appeared open, and yet, something strange began happening during the 1990s. The successor never arrived. At first, this absence did not feel alarming. Deep space missions naturally require many years of planning and development. Voyager itself had taken years to design before launch. But as time passed, the silence became more noticeable. No Voyager 3, no replacement Grand Tour, no new generation of broad outer solar system exploration. Instead, NASA and other space agencies slowly moved toward a different style of mission design, more focused, more specialized, more precise. Galileo travelled to Jupiter and remained there studying the system in detail for years. Cassini later orbited Saturn in one of the greatest scientific missions ever conducted. New Horizons eventually reached Pluto after an extraordinary journey across the solar system. These missions were remarkable achievements, but philosophically, they were different from Voyager. Voyager had been exploratory in the broadest sense of the word. It swept outward through the unknown, surveying entire planetary systems one after another. The mission behaved almost like an expedition ship mapping coastlines no civilization had previously seen. The newer missions resembled scientific laboratories, careful, targeted, deeply optimized. Instead of asking, "What is out there?" they increasingly asked, "How exactly does this specific world work?" Scientifically, this approach made perfect sense. As knowledge grows, specialization naturally follows. Once humanity learned the outer planets were complex, researchers wanted detailed answers rather than brief glimpses. But something subtle changed alongside that scientific evolution. Breadth gave way to depth. And in the process, the particular spirit embodied by Voyager slowly became harder to reproduce. There were practical reasons for this transformation too. Modern missions became vastly more complicated. Computers improved dramatically, but expectations also expanded. Scientists demanded higher resolution instruments, larger data volumes, longer operational lifetimes, and increasingly precise navigation, safety reviews multiplied, budgets grew larger, development timelines stretched longer, complexity accumulated quietly over decades. In a strange paradox, humanity became technologically more advanced, while simultaneously finding certain kinds of ambitious exploration more difficult to sustain. Voyager had succeeded partly because it emerged during a transitional era. The spacecraft was sophisticated enough to travel outward successfully, yet still simple enough to remain relatively lightweight, adaptable and affordable compared to many later missions. Their limitations became strengths. There is something almost ironic about that. Sometimes civilizations move forward not in smooth straight lines, but through temporary windows where technology, economics and imagination briefly align in unusual balance. Voyager belonged to one of those windows, and by the 1990s many of the conditions that created it had already faded. The Cold War was ending. NASA's budget remained constrained. The shuttle program consumed enormous institutional attention. Political leaders increasingly prioritized shorter-term results. Risk tolerance declined steadily after disasters like Challenger. Meanwhile, robotic exploration itself had become more professionalized and carefully managed. That may sound positive, and in many ways it was. Spacecraft became extraordinarily capable. Scientific returns became deeper and more precise, but highly optimized systems often become cautious systems, and caution changes the emotional texture of exploration. Voyager carried uncertainty almost casually. The mission accepted enormous unknowns because nobody had ever explored those regions before. Modern missions increasingly try to minimize uncertainty before launch. That shift altered not only engineering, but imagination itself. The difference is subtle, yet important. Voyager explored because humanity wanted to see what existed. Many later missions explored because humanity already knew enough to formulate very specific scientific objectives. Both approaches are valuable, but they feel different emotionally. One resembles wandering into unknown wilderness. The other resembles conducting careful research inside territory already partially mapped. As the years continued passing after Neptune, another realization slowly emerged among planetary scientists. Uranus and Neptune remained profoundly understudied. Voyager 2's flybys lasted only brief periods during its enormous journey. The spacecraft captured extraordinary discoveries, but only snapshots. No orbiter stayed behind. No atmospheric probe descended deeply into the planets. No submarine explored hidden oceans beneath icy moons. For decades afterward, humanity's understanding of the ice giants remained strangely incomplete. In fact, astronomers eventually discovered that Neptune-sized planets appear extremely common throughout the galaxy around other stars, which created a remarkable irony. Humanity was beginning to identify distant exoplanets light years away, while still barely understanding two major planets inside its own solar system, and still, no Voyager 3 appeared. The absence slowly became part of the background of modern space exploration. People stopped expecting a successor because enough time had passed that Voyager itself began feeling less like the beginning of something, and more like a unique historical moment unlikely to return. A mission from another age. A brief era when civilizations still believed the future would naturally continue expanding outward forever. It is tempting to explain Voyager entirely through physics. After all, the mission depended on a real astronomical event. Jupiter, Saturn, Uranus and Neptune moved into a rare arrangement that allowed gravity assist to carry spacecraft outward from one world to the next. Without that alignment, the mission would have been vastly more difficult. That part is true, but over time, many historians and scientists began realizing something deeper. the planets were not the only things that aligned. Humanity aligned too. And perhaps that alignment was even rarer. Because when we look carefully at the Voyager era, we begin to notice how many separate conditions briefly move together in the same direction. Political conditions, economic conditions, technological conditions, institutional conditions, psychological conditions, like gears inside a great machine, suddenly locking together for a short period of time before drifting apart again. The United States was willing to spend enormous amounts of money on science and engineering because of Cold War competition. Large aerospace industries already existed because of military and Apollo programs. A generation of highly experienced engineers had recently learned how to build deep space systems. Public imagination remained captured by the idea of space exploration. And culturally, the future still felt expansive. All of those conditions mattered. Remove enough of them, and Voyager likely never happens. There is something strangely humbling about that realization. Civilizations often imagine their achievements as inevitable products of intelligence and progress. But history is rarely inevitable. Great projects emerge from fragile combinations of circumstance. A small political shift, an economic recession, a cancelled budget meeting, a national tragedy. Any of these can quietly alter the future for decades. Voyager happened partly because the 1960s and 70s produced a civilization temporarily comfortable with enormous ambition. Not perfectly comfortable, of course. There were fierce political battles over funding and priorities even then. But large sections of society still believed technological progress naturally expanded horizons. Many people genuinely expected humanity to continue moving outward after Apollo. Permanent moon bases, Mars expeditions, gigantic space stations, interplanetary travel. Some of those expectations now seem overly optimistic, almost innocent. But optimism itself can become a powerful historical force, because ambitious civilizations often attempt things cautious. Civilizations never begin. And Voyager carried traces of that older optimism inside its design philosophy. The spacecraft accepted uncertainty. The mission embraced long timelines. The engineers prepared for possibilities beyond official requirements. Scientists pursued exploration not because every outcome was predictable, but precisely because it was not. That emotional attitude mattered enormously, especially because exploration itself is psychologically unusual. Most systems in human life reward short-term results. Governments focus on election cycles. Companies focus on quarterly profits. News cycles move by the hour. Public attention shifts constantly toward immediate concerns. But deep space exploration operates on very different timescales. Voyager launched in 1977. Neptune was not reached until 12 years later. Interstellar space arrived decades afterward. The spacecraft may continue drifting through the galaxy long after every person involved in their launch has died. Very few human institutions think comfortably across such spans of time, and this creates a quiet tension inside modern civilization. Humanity possesses technology powerful enough to explore enormous distances, but maintaining commitment across decades may be even harder than building the machines themselves. There is an old architectural tradition in parts of Europe where builders began constructing cathedrals knowing the work might continue long after they themselves were gone. Some craftsmen spent their entire lives helping create buildings they would never see completed. Deep space exploration resembles that kind of thinking. Voyager required thousands of people contributing effort toward outcomes they might never personally witness. And for a brief historical moment, enough people accepted that bargain. But the alignment did not last. Slowly, the forces supporting Voyager began weakening. The Cold War evolved, economic pressures increased, political attention fragmented. NASA's institutional culture shifted toward operations and risk management. Public fascination with space became less universal and more intermittent. None of these changes happened all at once. That is important. Exploration eras rarely collapse dramatically in a single moment. More often, they fade gradually, budget by budget, retirement by retirement, cancelled proposal by cancelled proposal, like a fire cooling slowly after midnight. And because the process unfolds gradually, societies often do not notice the change clearly until years later. By then, the momentum may already be gone. This fragility becomes especially visible when we compare Voyager to later missions. Modern spacecraft are often more scientifically capable in specific ways. Their cameras are sharper, their instruments more sensitive, their onboard computers incomparably more powerful, and yet missions resembling Voyager remain extremely difficult to approve. Why? Because Voyager was not merely a technical achievement, it was an institutional mood. A civilization temporarily willing to spend enormous effort exploring unknown regions simply because curiosity itself still carried political weight. That kind of motivation is difficult to quantify inside modern systems built increasingly around measurable efficiency and carefully justified outcomes. Today, many missions must demonstrate extremely detailed scientific returns before approval. Risks are minimized aggressively, budgets undergo years of scrutiny, objectives become highly specific. Again, none of this is irrational. Modern missions produce extraordinary science, but broad exploratory surveying, the kind Voyager represented, becomes harder in environments optimized for predictability. And perhaps that is why Voyager now feels emotionally different from many later missions. The spacecraft carried uncertainty openly. Nobody knew exactly what waited at Jupiter. Nobody predicted Io's volcanoes. Nobody expected Triton's geysers. Nobody fully imagined Europa's hidden ocean possibilities. Voyager discovered not only answers, but entirely new categories of mystery. There is something deeply human in that style of exploration, the willingness to travel outward before fully knowing what questions should even be asked. And maybe that is part of why the mission continues haunting people decades later, because Voyager reminds us that civilizations occasionally enter brief periods where curiosity becomes larger than caution, moments when entire societies lean forward together toward the unknown. The planets aligned once every 175 years. But perhaps the more extraordinary alignment was the temporary moment when human beings aligned with them too. After Voyager completed its journey across the outer planets, one difficult reality slowly returned to the center of planetary science. The rare alignment was gone. Jupiter, Saturn, Uranus and Neptune continued moving along their immense orbits around the Sun, drifting gradually out of the positions that had once allowed Voyager to leap elegantly from world to world through gravity assists. The hidden doorway inside the solar system had closed again, and without that alignment, the scale of deep space travel changed dramatically. A mission launched directly toward Uranus or Neptune now faced much longer travel times. Engineers could still use carefully planned gravity assists in some situations, of course, but the beautifully efficient chain Voyager used no longer existed in the same way. The distances returned to feeling enormous. Neptune alone orbits roughly 3 billion miles from the Sun. Even light, moving at the fastest speed nature allows, requires hours to travel between Neptune and Earth. Human intuition struggles with distances like these because everyday life contains almost nothing comparable. You can walk across a room in seconds, cross a city in an hour, fly across oceans in a day. But deep space moves differently. Voyager travelled for 12 years before reaching Neptune. 12 years. A child entering elementary school at launch could already be preparing for adulthood by the time the spacecraft arrived, and that timescale creates a problem far stranger than engineering: patience, or more precisely, institutional patience. Because deep space exploration demands a style of thinking modern societies often find difficult to sustain comfortably. Governments change constantly, administrations shift, budgets rise and fall, public attention drifts from crisis to crisis, but interplanetary exploration unfolds slowly and without urgency. Spacecraft do not care about election calendars. The outer planets continue orbiting in silence regardless of political speeches or economic cycles back on Earth. This creates a subtle tension between civilization and cosmos. The universe operates comfortably across centuries and millions of years. Human institutions often struggle to think beyond a few years at a time, and so missions like Voyager become unusually difficult to justify politically, even when the science is extraordinary. Imagine planting a forest knowing you will never live long enough to walk beneath its mature trees, or writing letters that may not arrive until after your retirement. Deep space missions ask civilizations to think that way. The people approving funding may never personally witness the greatest discoveries. The engineers designing instruments might already be elderly by the time the spacecraft reaches its destination. Some scientists involved at launch may not survive long enough to see the mission completed. There is something emotionally unusual about working on projects stretched across human generations, and yet, many of humanity's most meaningful achievements depend on exactly this kind of long-horizon thinking. Ancient observatories, cathedrals, libraries, great bridges, space telescopes. They all require societies willing to invest effort into futures extending far beyond immediate reward. Voyager belonged to that tradition. But after the 1980s, sustaining that mentality became increasingly difficult, partly because modern political systems became faster and more reactive. Television accelerated news cycles, then computers accelerated information itself, then the internet accelerated attention even further. Public focus fragmented into smaller and shorter moments. Meanwhile, deep space exploration remained stubbornly slow. A spacecraft crossing billions of miles cannot adapt itself to the rhythm of social media, financial quarters, or election seasons. It simply continues drifting outward through darkness year after year. There is something almost meditative about that contrast. Civilization rushing constantly, while Voyager moves patiently through silence. And patience becomes especially difficult when missions grow more expensive. Without the rare efficiencies of the Grand Tour alignment, future outer planet missions often required either longer travel times or larger rockets and more fuel. Both possibilities increased costs and political risk. Imagine proposing a mission expected to arrive at its destination 20 or 30 years after launch. Not merely operate for 30 years, arrive after 30 years. That is difficult for institutions to emotionally process, because modern systems prefer feedback quickly, results, metrics, visible progress. But deep space exploration often spends years appearing almost motionless to the public. Spacecraft coast quietly through emptiness, while engineers make tiny trajectory corrections and patiently monitor systems millions or billions of miles away. The work is real, the science is real, the achievement is immense, but much of it unfolds invisibly. This invisibility matters more than many people realize. Human beings are emotionally motivated by visible momentum. We like watching progress happen. We enjoy countdowns, launches, arrivals, dramatic images. Voyager contained those moments too. But between them existed vast stretches of waiting. And waiting is difficult for civilizations organized increasingly around speed. Even scientists themselves sometimes worried about this problem. A mission delayed too long might lose political support entirely before launch. Technology designed at the beginning of development could already feel outdated by arrival. Younger researchers entering the field might hesitate to dedicate careers to projects requiring decades before major scientific returns appeared. Time itself slowly became an adversary, not because the spacecraft could not survive long enough. Voyager proved they often could, but because civilizations struggle to sustain emotional continuity across such enormous spans. There is an irony hidden here. Human beings evolved beneath stars moving slowly across the night sky. Ancient cultures built calendars around planetary motion and seasonal cycles unfolding over years. For most of history, people understood time through agriculture, weather, migration, and generations. Modern civilization, by contrast, increasingly experiences time through acceleration, faster communication, faster transportation, faster markets, faster information, and yet the solar system remains ancient and slow. The planets cannot be hurried. Jupiter still requires nearly 12 Earth years to complete one orbit around the Sun. Neptune needs more than 160 years. The outer darkness moves at its own pace. Perhaps that is part of why Voyager still feels emotionally powerful today. The spacecraft remind us that some journeys remain too large for instant gratification. Some discoveries require patience measured not in hours or months, but in decades. And for a brief period during the 1970s, humanity accepted that bargain. It accepted uncertainty, delay, distance, silence. Not because rewards would come quickly, but because curiosity itself was considered worth the wait. But while Voyager continued patiently outward through deep space, the institution that launched it was slowly becoming something very different from the agency that first imagined the Grand Tour. As the 1980s unfolded, NASA was becoming an increasingly different organization from the one that launched Voyager. The change did not happen all at once. There was no single meeting where someone announced that deep space exploration no longer mattered. No dramatic speech declaring the end of outward ambition. Instead, the transformation unfolded gradually, almost invisibly, mission by mission, budget by budget, priority by priority. And at the center of this transformation stood the space shuttle. When the shuttle first entered service, many people believed it represented the future of spaceflight. The spacecraft looked elegant and futuristic, a reusable vehicle gliding back through Earth's atmosphere like something from science fiction finally becoming real. NASA hoped the shuttle would make access to orbit routine, frequent launches, large cargo delivery, scientific laboratories in space, satellites repaired and upgraded in orbit. The vision was ambitious in its own way, but maintaining the shuttle program required enormous amounts of money, personnel, infrastructure, engineering attention, and political energy. Launch facilities needed constant maintenance. Flight schedules demanded coordination. Safety reviews multiplied. Hardware refurbishment consumed resources after every mission. Over time, the shuttle became less like a single spacecraft and more like an entire ecosystem, absorbing much of NASA's institutional focus. And while astronauts repeatedly travelled a few hundred miles above Earth, the outer planets grew quiet again. This shift affected planetary science profoundly. Voyager had created excitement across the scientific community. Young researchers entered the field inspired by the images arriving from Jupiter, Saturn, Uranus, and Neptune. Entire careers formed around new questions Voyager uncovered, but inspiration alone cannot sustain exploration. Scientists still needed spacecraft, instruments, funding, mission approvals, and during much of the 1980s those opportunities became painfully scarce. Between the launches of Voyager and Galileo, the United States experienced an extraordinarily long drought in major planetary exploration missions. Years passed with no new outer planet spacecraft leaving Earth. For younger scientists entering the field, this created a strange atmosphere of uncertainty. The discoveries remained revolutionary, but the pathway forward felt unclear. Some mission concepts were proposed enthusiastically and then quietly cancelled. Others survived for years in planning stages before budget pressures weakened them again. Teams formed, dissolved, reorganised, and waited. There is something emotionally difficult about watching ideas slowly fade in committee rooms, not because they failed scientifically, but because institutional momentum disappeared around them. And then, in January of 1986, another shock changed NASA even more deeply. The Space Shuttle Challenger broke apart shortly after launch. Millions of people watched the disaster live on television. For many Americans, the event felt psychologically devastating. The shuttle had been presented as reliable and increasingly routine, almost like an operational transportation system rather than an experimental spacecraft. But spaceflight is never routine. The disaster shattered that illusion instantly. Inside NASA, the emotional consequences were enormous. Investigations followed, schedules collapsed, confidence weakened, safety culture intensified dramatically. And once again, none of these reactions were irrational. 7 astronauts had died in front of the world. Of course, the agency became more cautious afterward. But caution changes institutions over time. Risk tolerance shrinks. Approval systems expand. Technical reviews multiply. Ambitious proposals become harder to defend politically. Exploration slowly becomes more conservative. This shift mattered especially for Voyager-style missions, because those missions naturally contain uncertainty. Voyager succeeded partly because engineers accepted that many unknowns could only be solved during the mission itself. The spacecraft entered environments humanity had never encountered before. Surprises were expected, but after Challenger, institutional tolerance for uncertainty diminished sharply across much of NASA. The agency increasingly prioritized predictability, operational discipline, and carefully managed risk. Again, this was understandable, but it also made broad exploratory missions more difficult to sustain. Meanwhile, another quieter process was unfolding beneath the surface. Institutional memory was beginning to fade. The engineers who built Voyager slowly retired. Apollo-era specialists left the workforce. Manufacturing systems changed. Contractors disappeared. Technical expertise scattered across different programs. This process is easy to underestimate because knowledge often feels permanent when written in books or stored inside computers. But complex engineering knowledge frequently lives inside people, inside habits, experience, conversations, instincts developed over decades. When exploration pauses long enough, those invisible systems of knowledge begin dissolving quietly. A generation learns how to build something extraordinary, then gradually loses opportunities to practice those skills again. Voyager itself became a strange example of this problem years later. Some of its software systems used programming methods already becoming old-fashioned by modern standards. Engineers maintaining the spacecraft decades afterward sometimes found themselves studying documentation and coding structures that younger specialists rarely encountered anymore. It was almost like preserving an ancient machine built in a technological dialect slowly fading from living memory. And yet, despite all this, the desire to explore never disappeared entirely. Planetary scientists continued proposing missions, engineers continued imagining spacecraft, researchers continued studying Voyager's discoveries with growing fascination. The curiosity survived, but curiosity alone is not enough. Exploration requires continuity, momentum, supply chains, training pipelines, institutional confidence, long-term funding structures, political patience. And once those systems weaken, restarting them becomes surprisingly difficult. It resembles keeping a fire alive during winter. A strong fire can warm an entire room easily, but if the flames shrink too far, rebuilding them requires effort, fuel, and careful attention all over again. By the late 1980s and early 1990s, planetary science had survived, but the great outward momentum of the Voyager era had cooled substantially. The missions that eventually emerged afterward would still achieve extraordinary discoveries, but they would operate according to a different philosophy of exploration entirely. As the momentum of the Voyager era slowly faded, planetary science entered a quieter and more careful phase. The age of sweeping outward surveys was ending. In its place emerged something more focused, more precise, more patient, and no mission symbolized that transformation more clearly than Galileo. Launched in 1989, the same year Voyager 2 reached Neptune, Galileo was designed for a very different style of exploration. Voyager had behaved almost like a traveller moving quickly through unfamiliar lands, gathering glimpses of many worlds before continuing onward into darkness. Galileo was built to stay. Its destination was Jupiter, and instead of simply flying past the planet, the spacecraft would enter orbit and spend years studying the Jovian system in extraordinary detail. This distinction may sound subtle at first, but it reflected a profound shift in scientific philosophy. Voyager asked, "What is out there?" Galileo increasingly asked, "How exactly does this one place work?" The change made sense scientifically. Voyager had revealed something astonishing. The giant planets were not simple worlds that could be understood through brief encounters alone. Each system contained enormous complexity: weather, chemistry, magnetic fields, geology, radiation, hidden oceans, dynamic moons, and processes unfolding across vast spans of time. A quick flyby could reveal wonders, but long-term orbiters could reveal behaviour. And behaviour matters deeply in science. A single photograph captures a moment. Years of observation reveal patterns. So Galileo arrived at Jupiter not merely as an explorer, but almost as a patient observer settling into a long scientific conversation with an alien planetary system. The mission itself endured a difficult beginning. Shortly after launch, Galileo suffered a major technical problem when its large communication antenna failed to unfold correctly. The spacecraft suddenly lost the high-capacity communication system scientists expected to use for transmitting enormous amounts of data back to Earth. For many missions, such a failure might have become catastrophic. But Galileo's engineers adapted carefully. Data transmission slowed dramatically, yet the mission survived through extraordinary efforts to redesign communication strategies and compress scientific information more efficiently. There is something quietly admirable about that resilience. Deep space exploration repeatedly reveals the same truth. Perfection is rare. Adaptation is essential. And Galileo adapted beautifully. When the spacecraft finally reached Jupiter in 1995 after a long journey involving multiple gravity assists through the inner solar system, it began transforming humanity's understanding of the Jovian system once again. This time not through brief revelation, but through sustained attention. Galileo watched storms evolve across Jupiter's atmosphere over long periods. It studied magnetic interactions between the planet and its moons. It observed volcanic eruptions on Io repeatedly instead of only during fleeting encounters. And perhaps most importantly of all, it strengthened the growing case for hidden oceans beneath Europa's icy crust. Voyager had provided the first hints. Galileo deepened the mystery. The spacecraft detected evidence suggesting that beneath Europa's frozen surface rested a vast saltwater ocean warmed internally by tidal forces generated through Jupiter's gravity, an ocean potentially containing more liquid water than all of Earth's oceans combined. Hidden beneath ice, far from sunlight, possibly stable for immense spans of time, the implications felt enormous. For centuries, human beings assumed life required warm sunlight and Earth-like conditions. But Europa suggested something stranger. Perhaps life could emerge in darkness too. Perhaps oceans hidden beneath ice might remain biologically active. Perhaps habitable environments exist in places humanity once dismissed entirely. Today, many scientists consider Europa one of the most promising locations in the solar system for searching for extraterrestrial life, and Galileo helped transform that idea from speculation into serious scientific possibility. Yet while the mission expanded scientific understanding magnificently, it also reflected the changing economics and psychology of exploration. Galileo was extraordinarily capable, but it was also expensive, technically complex, and time-consuming to develop. The spacecraft carried sophisticated instruments, radiation protection systems, advanced onboard computers, and intricate orbital planning requirements. Years of preparation preceded launch. Years more passed before arrival, and this pattern would increasingly define modern planetary science. Missions became fewer, but deeper, more specialized, more precise, more optimized around carefully chosen scientific goals. In some ways, planetary exploration matured, but maturity changes emotional atmosphere. Voyager often felt improvisational and wide-eyed, almost like humanity wandering through unknown wilderness for the first time. Galileo felt more methodical, more surgical, not less inspiring, but differently inspiring. Like the difference between a sailor crossing uncharted oceans and a biologist spending years studying a single rainforest carefully enough to understand its hidden systems. Both journeys contain wonder, but the texture of that wonder changes, and perhaps inevitably, precision carried costs. The more specialized missions became, the harder they were to approve politically. Scientific instruments grew more advanced, development timelines stretched longer, risk management systems expanded, mission planners demanded increasingly detailed justifications before launch approval. The era of broad exploratory surveying slowly gave way to targeted scientific investigation. Again, this shift was not a mistake. The science produced by missions like Galileo became astonishingly rich. Humanity learned more about Jupiter and its moons than Voyager alone could ever reveal. But something subtle faded too. Voyager had explored because the unknown itself felt valuable. Galileo explored because scientists already knew enough to ask very precise questions. That distinction matters emotionally. One style of exploration is driven by open-ended curiosity, the other by disciplined investigation. And as the 1990s continued unfolding, this newer philosophy gradually became the dominant model for planetary science. The solar system was no longer treated primarily as unexplored territory. It became a collection of highly specialized scientific environments demanding long-term study. The age of wandering lanterns drifting broadly through darkness was giving way to the age of microscopes, and soon another mission would carry that philosophy even farther outward, towards Saturn, Titan, and worlds stranger than Voyager ever imagined. By the time the Cassini mission began its long journey towards Saturn in the late 1990s, planetary science had fully entered a new era. The broad reconnaissance age of Voyager had transformed into something more focused and deliberate, and in many ways, the scientific results became even more astonishing. Cassini was magnificent. The spacecraft represented decades of engineering refinement and international cooperation between NASA, the European Space Agency, and the Italian Space Agency. Its instruments were dramatically more advanced than those carried by Voyager. Its cameras captured details of Saturn and its moons with breathtaking clarity. Its computers, navigation systems, and scientific tools reflected an entirely different technological generation. But all that sophistication carried a price. Cassini became one of the most expensive and complex robotic exploration missions ever attempted, and that complexity revealed something important about the changing nature of exploration itself. As humanity learned more about the solar system, spacecraft increasingly evolved from wandering scouts into highly specialized laboratories. Voyager had flown past Saturn quickly, gathering an extraordinary flood of discoveries before continuing onward into deep space. Cassini stayed for years. It orbited Saturn again and again, studying seasonal changes, atmospheric motion, magnetic interactions, ring dynamics, and the intricate behavior of moons drifting through the planet's enormous gravitational system. The difference resembled returning to a mountain range not merely to photograph it, but to live there long enough to understand its weather, rivers, wildlife, and changing seasons. And Saturn rewarded that patience beautifully. Cassini revealed astonishing complexity inside the ring system. What once appeared through telescopes as elegant flat bands turned out to contain waves, gaps, ripples, collisions, temporary structures, and interactions unfolding continuously across millions of icy fragments. The rings were not static objects. They behaved almost like living systems. Meanwhile, Titan, once hidden beneath orange haze during Voyager's flyby, slowly emerged in extraordinary detail. Cassini discovered rivers, lakes, rainfall, cloud systems, shorelines, not made of water, but liquid methane and ethane, an alien hydrological cycle unfolding beneath dim orange skies. There is something deeply strange and beautiful about Titan. If Earth is a world shaped by water, Titan is almost like a colder dream version of the same idea, where chemistry follows familiar patterns using unfamiliar materials. Rain still falls, rivers still carve landscapes, lakes still gather in low places, but the temperatures are so cold that water behaves like rock, while hydrocarbons flow like liquid. And then there was Enceladus, a small icy moon that many scientists once assumed would be relatively unremarkable. Instead, Cassini discovered enormous plumes erupting from fractures near the moon's south pole. Water vapor, ice particles and organic compounds blasted outward into space from beneath the frozen crust. Another hidden ocean, another potentially habitable environment, another reminder that the solar system kept becoming stranger the more carefully humanity observed it. Cassini's discoveries were so rich that entire generations of scientists built careers around analysing its data. And yet, despite all this success, another truth quietly emerged alongside the scientific triumphs. Missions like Cassini were becoming incredibly difficult to create, not because humanity lacked intelligence or technology, but because precision itself demands resources, more instruments, more testing, more radiation protection, more software, more safety reviews, more years of development, more layers of oversight. Modern spacecraft became astonishingly capable, but also increasingly heavy with complexity. Voyager now looked almost simple by comparison, and strangely enough, that simplicity had once enabled boldness. The Voyager spacecraft carried relatively limited computers, lower resolution instruments, and smaller data systems compared to later missions. But because they were lighter, simpler, and cheaper relative to their era, NASA could attempt something broader, a sweeping journey across multiple planetary systems. By contrast, later missions often focused intensely on a single destination because the spacecraft themselves became such enormous investments. The emotional texture of exploration changed with that shift. Voyager resembled a lantern carried into darkness, illuminating many distant shapes briefly as it continued forward. Cassini resembled a microscope, extraordinarily powerful, but carefully focused on one intricate environment at a time. Neither approach was superior in every way. One favoured breadth, the other depth. One discovered unexpected mysteries rapidly, the other patiently unravelled complexity layer by layer. And perhaps humanity needed both styles. But economically, the newer style proved harder to sustain frequently. This became visible again with New Horizons. Launched in 2006, New Horizons finally carried humanity to Pluto after a journey lasting nearly a decade. For generations, Pluto had remained a tiny unresolved point of light at the edge of the known planetary system. Even through powerful telescopes, details remained blurry and uncertain. And then New Horizons arrived. The images stunned scientists almost immediately. Instead of a frozen dead world, Pluto revealed towering mountains of water ice, vast nitrogen glaciers, layered atmospheric haze, and landscapes appearing unexpectedly young and dynamic. Even at the edge of the solar system, geological activity persisted. Once again, exploration overturned assumptions. But New Horizons also revealed another emotional truth. The spacecraft moved through the Pluto system quickly, just as Voyager once flew past the giant planets. After years of travel, the closest encounter itself lasted only hours before the spacecraft continued outward into darkness. There is something bittersweet about flyby missions, a decade of waiting, a few hours of revelation, then departure forever. And perhaps that feeling carried special weight, because by the early 21st century, missions like Voyager already seemed increasingly impossible to repeat. The economics had changed, institutional structures had changed, public attention had changed. Space exploration still continued brilliantly, but not with the same sweeping outward momentum of the Grand Tour era. And beneath all these transformations, another quieter problem had also begun emerging. One hidden far from public attention, inside aging industrial systems and forgotten corners of Cold War infrastructure. A problem involving heat, tiny amounts of heat, slowly fading inside the darkness between planets. Far beyond Mars, sunlight begins to weaken dramatically. Near Earth, solar panels work beautifully. Satellites unfold wide metallic wings and quietly drink energy from the sun. Even relatively small panels can provide enough electricity to power cameras, computers, scientific instruments, and communication systems. But the farther a spacecraft travels outward, the thinner sunlight becomes. By Jupiter, the sunlight is already much weaker than what reaches Earth. By Saturn, daylight resembles a dim overcast afternoon. Near Neptune, the sun itself shrinks into a brilliant but distant star, bright enough to see clearly, yet far too weak to easily power large spacecraft through solar energy alone. This created one of the great hidden challenges of deep space exploration. How do you keep a machine alive in darkness for decades? Voyager solved that problem through warmth, not roaring heat, not glowing reactors, just small, steady warmth, slowly produced through radioactive decay. Inside each spacecraft rested a material called plutonium-238. Unlike the plutonium associated with nuclear weapons, this isotope was valued for a quieter reason. As it naturally decayed over time, it released heat continuously and predictably. The spacecraft converted some of that heat into electricity using specialized systems often called radioisotope power generators. The concept itself is strangely gentle, tiny fragments of radioactive material slowly cooling over decades. like embers hidden beneath ash, continuing to glow long after the fire itself appears calm. Those fading embers powered Voyager's instruments, computers, heaters, and communication systems as the spacecraft crossed billions of miles of space. Without them, the mission would have ended long before Saturn. And this same kind of deep space power system later became essential for many other missions travelling far from the Sun. Galileo, Cassini, New Horizons, Mars rovers operating through dusty winters. Again and again, long-duration exploration quietly depended on these small nuclear heat sources, but hidden beneath this technological success was a strange historical reality. The ability to produce plutonium-238 existed largely because of enormous industrial systems created during the Cold War, factories, reactors, specialized chemical processing facilities, highly trained workers, government infrastructure operating at vast scale. These systems were never built primarily for peaceful exploration. They emerged from military and nuclear competition between superpowers during one of the most tense periods in modern history. And yet, out of those vast geopolitical tensions came materials that eventually powered humanity's journeys into deep space. There is something deeply ironic about that. The same civilization capable of building nuclear arsenals also used fragments of that industrial knowledge to send tiny scientific machines toward the stars. But after the Cold War began fading, many of those industrial systems quietly disappeared. Reactors shut down, production lines ended, facilities aged, expertise retired, and gradually the supply of plutonium-238 became dangerously limited. Most people never noticed this problem at all. It unfolded almost invisibly, buried inside technical reports, government budgets, and long-term energy policy discussions far from public attention. But for planetary scientists and mission planners, the implications were enormous. Without reliable production of deep space nuclear power systems, entire categories of exploration became difficult or impossible. Outer planet missions, long-duration probes, landers operating far from sunlight, exploration in permanently shadowed environments, all depended on steady electrical power where sunlight alone could not easily sustain machines. This is one of the strange truths about exploration. Great journeys often depend on invisible systems hidden far beneath the surface of public imagination. When people picture space exploration, they imagine rockets launching into the sky, astronauts floating weightlessly, or distant planets glowing against darkness. But beneath those dramatic images exists another world entirely. Supply chains, industrial chemistry, rare materials, specialized manufacturing, quiet engineering expertise accumulated over decades. Exploration is not built from inspiration alone. It also depends on infrastructure patient enough to sustain difficult work for generations. And infrastructure is fragile. Not fragile in the sense of weakness, but fragile in the sense that complex systems slowly decay when neglected long enough. A bridge abandoned eventually rusts. A language unused eventually fades. A scientific capability unsupported eventually disappears. The plutonium problem became one example of this broader pattern. Humanity still possessed the knowledge to build deep space probes. But maintaining the industrial foundation supporting those missions proved harder than many people expected. Eventually, efforts began restoring limited plutonium production in the United States. Scientists and engineers recognized that future exploration depended on preserving these capabilities before they vanish completely. But rebuilding old systems is rarely simple, especially when the original generation of specialists has already retired. There is a quiet sadness hidden inside that reality. Civilizations sometimes lose important capabilities not through catastrophe, but through gradual forgetting. Knowledge disperses slowly, priorities shift, expertise becomes rare, and one day people realize that something once considered ordinary has become difficult again. Voyager now seemed even more extraordinary in retrospect. The spacecraft emerged from a historical moment when many hidden systems briefly functioned together. The planetary alignment, Apollo-era engineering culture, Cold War infrastructure, political willingness to fund long missions, public fascination with exploration, industrial capacity capable of supporting deep space nuclear systems, like many rare ingredients combining into a single fleeting window of possibility. And still, despite all these challenges, Voyager itself continued drifting outward. The spacecraft moved patiently through darkness while their power slowly declined year after year. Each passing decade forced engineers to make difficult choices. Which instruments should remain active? Which heaters could be turned off safely? How much electricity could still be spared? The spacecraft gradually became quieter. Not dead, just quieter. Like elderly travelers speaking more softly as night grows deeper around them, and somewhere beyond the planets, beyond even the outer boundary of the sun's invisible influence, the old machines continued carrying their fading warmth into interstellar darkness. Long after the planets disappeared behind them, Voyager 1 and Voyager 2 continued travelling outward, past the orbit of Neptune, past the scattered icy debris of the Kuiper Belt, toward a boundary no human machine had ever crossed before, the edge of the sun's influence. This region is difficult to imagine because it does not resemble a wall or border in the ordinary sense. There is no giant line painted across space announcing the end of the solar system. Instead, the sun surrounds itself with an invisible bubble, a vast flowing region shaped by charged particles continuously streaming outward from the sun in every direction. This solar wind races through space carrying magnetic fields and traces of the sun itself far beyond the planets. For billions of miles, the solar wind dominates the surrounding environment, but eventually, the outward pressure weakens enough that interstellar space begins pressing back. Voyager spent years slowly approaching this invisible frontier, and then, in 2012, Voyager 1 crossed into interstellar space, humanity's first interstellar traveller. The moment itself was strangely quiet. No dramatic explosion, no sudden flash of light, no enormous cosmic gate opening in darkness. Only subtle changes inside streams of particles and magnetic measurements, arriving slowly through faint radio whispers from deep space. That gentleness somehow makes the achievement feel even more profound. A small machine built in the 1970s quietly drifting beyond the protective influence of its parent star, like a ship slipping silently beyond the edge of a familiar ocean into colder and deeper waters. Voyager 2 crossed the boundary several years later as well. Together, the spacecraft became the farthest artifacts humanity has ever created. And yet perhaps the most astonishing part of the story is not that they reached interstellar space. It is that they are still speaking to us at all. By now, Voyager's power systems have been fading for decades. The plutonium inside their generators continues decaying slowly, producing a little less heat and electricity every year. Engineers carefully monitor the remaining power almost like caretakers, rationing the final warmth of a campfire during winter. Every watt matters. Over time, difficult decisions became unavoidable. Certain instruments had to be turned off permanently. Some onboard heaters were shut down. Backup systems once kept available for emergencies were sacrificed to preserve energy elsewhere. Little by little, the spacecraft slowly grew quieter. There is something unexpectedly emotional about those decisions. Each instrument represented years of work by scientists and engineers, many of whom are no longer alive today. Entire careers were built around these machines, And now, decades later, modern engineers gently power systems down one by one, preserving the mission for just a little longer, like caretakers dimming lights room by room inside an ancient house. The distances involved make the situation even more extraordinary. Today, Voyager 1 sits so far from Earth that its radio signals travel for nearly an entire day before reaching us, and those signals are unimaginably faint. By the time Voyager's transmissions arrive at Earth, the energy contained within them is weaker than the tiny amount of light, landing on your skin from a distant star in the night sky. To hear Voyager at all, humanity relies on enormous radio antennas spread across Earth through a system called the Deep Space Network. Huge dishes listen carefully to the darkness. California, Spain, Australia. Together they take turns tracking the faint whispers of distant spacecraft as Earth rotates beneath the sky. There is something beautiful in imagining this. A civilization still listening carefully to machines launched nearly half a century ago. Even more remarkable, engineers have repeatedly found ways to rescue Voyager from problems nobody expected it to survive. Thrusters stopped behaving properly, aging systems drifted unpredictably, memory glitches appeared, tiny orientation errors threatened communication links, and again teams on Earth adapted creatively. Sometimes they revived backup systems untouched for decades. Sometimes they rewrote software for computers designed before the modern internet existed. Sometimes they searched through ancient technical documentation written by engineers who had already retired long ago. At one point, NASA engineers even restored thrusters that had not operated in decades, carefully reviving old systems to preserve the spacecraft's ability to point its antenna toward Earth. The effort felt almost archaeological, not simply operating technology, but rediscovering it. There is a quiet tenderness in these stories that often goes unnoticed in discussions about space exploration. Voyager is no longer merely a scientific mission. It has become a relationship across time. The engineers working on Voyager today are often younger than the spacecraft itself. Some were born years after launch, yet they spend their careers caring for machines built by an earlier generation, living inside a completely different historical world. A world of slide rules, Cold War politics, Apollo optimism, analog computers, hand-drawn engineering diagrams. And somehow, through all those decades of change, the conversation continues. Tiny signals crossing billions of miles, Earth listening patiently, Voyager answering softly. But the silence grows closer every year. Eventually, the remaining power will fall too low to operate communication systems at all. The spacecraft will continue drifting physically through the galaxy, but their voices will disappear. Engineers expect this final silence sometime during the early years of the 2030s. No dramatic ending will occur. The signals will simply weaken beyond recoverability. And one day, for the first time since 1977, Earth will stop hearing Voyager completely. The spacecraft will continue moving through interstellar darkness for millions of years afterward, long after continents shift, long after languages evolve, long after modern civilization itself changes into forms impossible to predict. The golden records will still remain attached quietly to their sides. Music, greetings, laughter, heartbeats, fragments of humanity carried endlessly through the galaxy. And perhaps that is why Voyager continues affecting people so deeply even now. The spacecraft feel less like machines and more like memories still travelling outward. Old travellers refusing to disappear quietly. Small artificial stars carrying the fading warmth of an earlier age of exploration into the cold between worlds. But the spacecraft are not the only things slowly fading. Back on Earth, something else has been growing quieter too. As Voyager drifts farther into interstellar darkness, another kind of distance becomes visible as well. Not distance measured in miles, but distance measured in generations. The civilization that launched Voyager no longer fully exists in the form it once did. The engineers who designed the spacecraft mostly belong to history now. Many of the scientists who first studied Voyager's images are elderly or gone. The political atmosphere that funded Apollo and the Grand Tour faded decades ago. Even the technological world surrounding Voyager has transformed almost beyond recognition. The spacecraft were built before personal computers became common, before mobile phones, before the internet connected much of the world, before digital life accelerated daily existence into the constant stream of information modern societies now inhabit. And yet Voyager continues drifting outward from that earlier era, carrying the emotional atmosphere of its time along with it. An age when humanity briefly believed the future would naturally keep expanding forever. That belief matters more than it may first appear, because civilizations do not explore continuously, they explore in bursts. History reveals this pattern again and again. There are periods when societies suddenly become outward-looking, curious, ambitious beyond immediate necessity. Ships cross unfamiliar oceans, new trade routes appear, telescopes are built, maps expand, explorers travel farther than previous generations believed practical. Then, slowly, something changes. Attention turns inward. Economic pressures rise. Institutions become cautious. Maintenance replaces expansion. Stability becomes more valuable than risk. The outward momentum softens. The age of sail eventually faded. The great polar expeditions slowed. The Apollo era ended. And in some ways, Voyager became part of that same pattern. Not a failure, not a collapse, a cresting wave. This is important to understand because many people instinctively imagine technological progress as permanent and linear. We assume each generation will naturally continue the unfinished ambitions of the previous one. But history rarely behaves so smoothly. Sometimes civilizations gain extraordinary capabilities briefly, and then choose not to use them in the same way again. Ancient Rome built massive concrete structures whose techniques were partially forgotten for centuries afterward. China launched enormous treasure fleets during the 15th century, then largely abandoned long-range maritime expansion. The Apollo program carried humans to the moon, and then humanity stopped returning there for generations. Capability alone does not guarantee continuation. Commitment matters too. Voyager existed because an unusual number of conditions aligned simultaneously. Political will, Cold War funding, Apollo-trained engineers, industrial infrastructure, public fascination with space, institutional tolerance for long-term uncertainty, a civilization emotionally oriented toward outward expansion. Over time, many of those conditions weakened, and perhaps most importantly, the emotional relationship between society and the future changed. The future once felt physically larger. That may sound strange, but many people living during the 1960s and 70s genuinely expected human civilization to spread steadily into space during the coming centuries. Space stations, moon bases, Mars expeditions, interplanetary settlements. These ideas appeared constantly in books, films, scientific discussions, and public imagination, not as fantasies, as expectations. But modern civilization often relates to the future differently. The future now feels faster, yet smaller. Technology advances rapidly, but much of that progress unfolds inside communication systems, software, automation, and digital infrastructure, rather than giant outward physical expansion. Civilizations change focus. And once focus changes long enough, institutional memory begins fading quietly. This process becomes especially visible in deep space engineering. Voyager's software systems were built using programming methods that now feel almost ancient. Some of the original documentation exists in aging archives and technical manuals written decades ago. Engineers maintaining the spacecraft sometimes study systems resembling a technological dialect few people still speak fluently. There is something almost archaeological about it. Modern engineers communicating with artifacts from an earlier civilization, preserving continuity across time, and yet no direct successor followed behind them. No new Voyager rising through the darkness years later. No second grand tour beginning quietly in the distance. No chain of interstellar explorers stretching outward generation after generation. Voyager remains alone. That loneliness gives the mission much of its emotional power. Because the spacecraft do not merely represent exploration, they represent a pause, a reminder that history moves unevenly. For all our extraordinary technological achievements, modern civilization still struggles with projects requiring patience across multiple generations. Democracies rotate leadership constantly. Economic systems reward immediate returns. Public attention shifts rapidly between crises and distractions. Meanwhile, the deep universe remains patient beyond comprehension. The stars are in no hurry. The planets continue orbiting slowly. Interstellar space waits silently. Voyager belonged to a style of thinking willing to move at cosmic speed instead of human speed. Slowly, patiently, without demanding immediate reward. Perhaps that is part of why the spacecraft feel almost spiritual to some people now. Not religious exactly, but reflective. Voyager reminds humanity of a version of itself that once looked outward with extraordinary seriousness. A civilization willing to spend decades crossing darkness simply to learn what existed there. And maybe that civilization has not vanished entirely. After all, people still dream about missions to Europa, Titan, and the ice giants. New telescopes continue searching distant planets around other stars. Young scientists still enter planetary science inspired by Voyager's images. Curiosity survives. It always seems to survive. But curiosity alone is not enough to sustain exploration on Voyager's scale. Civilizations must also choose patience, continuity, long-term commitment, and those choices are far rarer than intelligence. Somewhere tonight, beyond the edge of the sun's invisible influence. Voyager continues moving through the galaxy completely alone. No spacecraft follows behind it, only silence. And perhaps one quiet, unanswered question lingering back on Earth. Not whether humanity can build another Voyager, but whether humanity still remembers how to become the kind of civilization that would. Long after Voyager finished visiting planets, long after the cameras photographed Neptune and Triton for the final time, the spacecraft continued carrying something else through the darkness. A message. Bolted carefully to the side of each spacecraft rests a golden record protected inside an aluminum cover. At first glance, it resembles an ordinary vinyl music record from Earth's 20th century, though plated in gold to survive the long cold journey ahead. Inside those grooves exists an attempt, imperfect, hopeful, strangely human, to introduce an entire civilization to the cosmos. Music, greetings in dozens of languages, laughter, the sound of rain, footsteps, heartbeats, birdsong, whales singing beneath dark oceans, a baby crying, a kiss, fragments of Earth gathered together and launched into interstellar space. Carl Sagan and the small team helping create the record understood something important from the beginning. The chances of extraterrestrials ever finding Voyager are extraordinarily small. The galaxy is unimaginably vast. Even moving faster than 30,000 miles per hour, Voyager would still require tens of thousands of years merely to approach nearby stars. The spacecraft are tiny against the scale of interstellar distance. almost invisible. And yet the records were created anyway. Not because success was likely, but because the gesture itself mattered. There is something deeply moving about that. Human beings often create meaning through acts that may never receive answers. We write letters no one may read. We plant trees whose shade we may never sit beneath. We bury time capsules for strangers far in the future. We speak into silence, hoping someone, somewhere, may someday listen. The golden record belongs to that tradition. In many ways, the records were never truly intended for aliens alone. They were also messages to ourselves, a reminder that for one brief moment in history, humanity looked outward into the enormous darkness and decided to answer it not with weapons or fear, but with music, curiosity, mathematics, art, and greetings spoken softly across the void. And perhaps nothing captured that emotional perspective more powerfully than a photograph Voyager later helped create. The pale blue dot. In 1990, after Voyager 1 completed its planetary mission, Carl Sagan requested that the spacecraft turn its cameras backward one final time toward home. NASA hesitated initially. The cameras were old. The sunlight risked damaging sensitive instruments. Scientifically, the image offered little practical value, but eventually permission was granted. From billions of miles away, Voyager photographed Earth as a tiny speck suspended inside a beam of scattered sunlight, a pale blue dot, smaller than a pixel, almost nothing. And yet everything humanity had ever known existed there. Every civilization, every war, every love story, every empire, every scientist, every child, every piece of music ever written, every dream of the future, compressed into a fraction of light nearly swallowed by cosmic darkness. The image changed many people permanently, because Voyager had accomplished something strange. The farther the spacecraft travelled away from Earth, the more precious Earth itself began to appear. Exploration did not diminish humanity's importance, it softened humanity's arrogance. There is wisdom hidden inside that distinction. Sometimes people fear that cosmic exploration makes human life feel insignificant. But Voyager often produced the opposite emotional effect. The immense scale of the universe made Earth seem fragile, rare, beautiful, like a warm window glowing softly across an enormous winter landscape. And perhaps that emotional shift explains why Voyager continues resonating decades later. The spacecraft are scientific achievements, certainly, but they are also mirrors. When people look at Voyager, they often see questions about civilization itself reflected back at them. What kinds of futures do human beings choose? What happens when curiosity weakens? Can society still think across generations? What responsibilities come with technological power? What parts of humanity deserve carrying into deep time? Voyager never answered those questions directly, but it carried them outward, and tonight, even now, the spacecraft continued drifting through interstellar darkness. The stars ahead will move slowly over millions of years, long after Earth's continents reshape themselves, long after modern nations disappear, long after languages evolve into forms impossible for us to understand. Voyager may still exist somewhere between the stars, silent, cold, patient. The golden records will continue circling endlessly beside them, a tiny archive of a small world orbiting an ordinary star. There is something peaceful about imagining that. Not because Voyager makes humanity eternal, it does not. The spacecraft themselves will eventually erode under microscopic collisions with dust and radiation across immense spans of time. Nothing built by civilizations lasts forever. But Voyager reminds us that impermanence does not erase meaning. A song still matters even though it ends. A fire still gives warmth even though it fades. a civilization still matters even if its brightest eras pass briefly through history like comets crossing darkness. And perhaps that is the quiet lesson hidden inside the Voyager story. Exploration is not guaranteed. Curiosity is not automatic. Great outward journeys happen only when civilizations choose them. For one brief historical moment, humanity chose to reach outward toward the unknown with extraordinary courage and patience. The planets aligned, the engineers aligned, the institutions aligned, the imagination of an era aligned, and 2 small spacecraft slipped through the opening before it closed again. Tonight, they continue moving farther away than any human creation has ever travelled. No Voyager 3 follows behind them, only faint radio whispers crossing the darkness, and enormous antennas on Earth still listening carefully to the fading voices of machines launched nearly half a century ago. Perhaps someday another civilization-wide wave of exploration will rise again. Perhaps new spacecraft will return to Uranus, Neptune, and beyond. Perhaps humanity will once again choose futures measured not in quarterly reports or election cycles, but in generations. Or perhaps Voyager will remain what it already feels like to many people, a final lantern from an earlier age of optimism, still glowing softly while drifting out among the stars. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this quiet journey through the deep darkness beyond our world. If you would like to join me again for more gentle wanderings through science, space, and the mysteries that surround us, you're always welcome here. For now, though, the universe remains vast and patient above us, and somewhere out there tonight, Voyager continues onward through the silence, carrying a little piece of Earth into forever. Sleep peacefully wherever and whenever you may be.